we've talked about multiplying a matrix and a vector, we'll talk about multiplying two matrices. And we're going to show two ways how to do this, although they really are the same way. One of them is more practical to use whenever we're actually multiplying matrices, and the other one will be more practical to use during proofs. The first one we'll look at is the more practical one to use during proofs, but it does give us a nice extension of the matrix vector multiplication. I'm going to let A be an M by N matrix and B be an N by P matrix. So we need the number of columns in the first matrix to match the number of rows in the second matrix. Then we define the matrix multiplication AB as the matrix given by A times B1, A times B2, all the way up to A times BP, where these B vectors are the columns of my matrix B. So essentially, I'm going to multiply matrix A by each column vector of B. So let's look at an example of this. So here I have two matrices and I want to find the product. So I'm going to assume the one on the left is A and the one on the right is B. So the first step is to multiply my matrix A by the first column of B. As a reminder, I do this by multiplying entries of the vector by columns of the matrix and then adding them up. So I have 4 times the first column plus 0 times the second column minus 3 times the third column. That gives me 4 times -5 plus 0 times -3 minus 3 times -3, which is -11. For the second entry, I have 4 times 4 plus 0 times 4 minus 3 times 5, which is 1. So now I have a -11, 1. And that is going to correspond to my first column in the actual answer. The next thing we need to do is multiply this matrix by the second column. That's given by -7 times the first column plus 2 times the second plus 1 times the third. So I have -7 times -5 plus 2 times -3 plus 1 times -3, which gives me 26. For the second row, I have -7 times 4 plus 2 times 4 plus 1 times 5, which gives me -15. So now this is going to correspond to the second column of my solution. Finally, I'm going to do my matrix times the third column. So I have 9 times the first column minus 2 times the second column plus 1 times the third column. To get this, I have 9 times -5 minus 2 times -3 plus 1 times -3, which is -42. For the second row, I have 9 times 4 minus 2 times 4 plus 1 times 5, which is 33. So now, this corresponds to the third column of my solution, and I now have my answer. So this was a very long process. Our second method is going to try and make this a little bit simpler for us. So our goal is to multiply an M by N matrix A by an N by P matrix B. We're going to do this by looking at the entry in row I and column J of the product. This is found by multiplying row I in my matrix A by column J of the matrix B and then adding the resulting numbers. And as we do this, it'll seem like this method is a lot shorter and simpler. However, we're actually doing the exact same thing that we did in our previous method. We're just combining a lot of the steps into one. So let's look at an example. So here I have two matrices I want to multiply. And we're going to take this step by step. For the first entry, it's going to be in row 1, column 1. I need to multiply row 1 by column 1 and then add those numbers. So I have 3 times 0 is 0. 6 times 4 is 24. And 1 times 1 is 1. So that gives me my first entry. The next thing I want to find is still in row 1, but now I'm in the second column. So I have 3 times 1 is 3. 6 times 2 is 12. And 1 times 4 is 4. I'm now going to look at the first row and the third column. 3 times 6 is 18. 6 times -5 is -30. And 1 times 5 is 5. I now have the entire first row. I'm now going to move to my second row in the first column. 4 times 0 is 0. -4 times 4 is -16. -7 times 1 is -7. I now have my second row, second column. 4 times 1 is 4. -4 times 2 is -8. And -7 times 4 is -28. From there, I'm going to go second row, third column. 4 times 6 is 24. -4 times -5 is 20. And -7 times 5 is -35. I'm now completely done with my second row. So I want to move to my third row, and I'm start with the first column. -4 times 0 is 0. -3 times 4 is -12. And 9 times 1 is 9. I now move to my second column. -4 times 1 is -4. -3 times 2 is -6. 9 times 4 is 36. And finally, I'm going to do my third row, third column. -4 times 6 is -24. -3 times -5 is 15. And 9 times 5 is 45. Now that I've done all that, it's just a matter of simplifying and adding up these numbers. And once I do that addition, I have my final result. There are a few warnings that we need to watch out for. Things that in matrix multiplication we want to be true, but are not true. First, in general, AB is not equal to BA. I cannot switch the order of multiplication when it comes to matrices. The next one, AB equal to AC does not mean that B is equal to C. I do not have the cancellation property. I can't just divide both sides by A. And finally, AB equal to 0 does not mean A is equal to 0 or B is equal to 0. Just because I multiply two matrices and get 0 does not mean one of the matrices had to be 0 to start with. It's entirely possible in matrices to multiply two non-zero things and still get a 0 answer. While these are things we should watch out for, let's look at things that we actually do know is true. The first one, A times BC is equal to AB times C. While I don't have commutativity, I do have associativity. So we do know that this one is true, assuming that A, B, and C have appropriate sizes for this to be defined in the first place. The next one is a distributive property. A times B plus C is equal to AB plus AC. And equivalently, we have that B plus C times A is equal to BA plus CA. Like I said, we do not have commutativity, so we can't change the order of multiplication. So we need to pay attention if we're multiplying on the left or on the right. The first one says we're multiplying by A on the left, the second one by A on the right. Finally, if I let R be a scalar, then this last property says it doesn't matter when I multiply the scalar. I can multiply A times B and then do the scalar. I can multiply the scalar by A and then multiply by B, or I can do the scalar times B and then do AB. So I can move the scalar appropriately.